Thank you very much. Bye-bye.
Hello students, welcome back to Physics 102 lecture. Before we proceed, I would like to take us back a bit on what we have discussed previously on electric charge. In our last lecture, we established that electric charge is conserved and is quantized. Okay? We know that it can't be created and nor destroyed. So the big question now is, how do we actually move a charge around? This is a very important question that we have to ask ourselves. If we claim that a charge cannot be created or destroyed, so how do we move a charge around? Okay, so the next question, for instance, is how does an object go from being neutral to having a net positive or negative charge? If we look at the slides, you will see that there are exactly three ways to transfer charge. One by friction, two by conduction, and three by induction. Okay? So let's break this down one by one, because understanding these mechanisms is going to explain everything from why we maybe our socks stick together in the dryer, for instance, or how a massive lightning storm gets generated. Okay? So if we talk about charging by friction, in other words, we are talking about rubbing something, maybe iron rod or a metal rod or a rubber rod, with another body. So let's start with the most common method we experience in our daily life, friction, or simply rubbing two different materials together, as I mentioned. So when you rub two different materials against each other, you are physically bringing their surface atoms into incredibly close contact. Yes. So the atoms of one material will naturally have stronger grip at higher affinity for electrons than the other. So because of this, electrons are transferred directly from one material to the other. Okay? Remember, this rule, I'll write it down. The material that loses electrons ends up with a deficit of negative charge. In that case, it becomes positively charged. Second rule or condition, the material that gains those electrons end up with an excess so that it becomes negatively charged. Okay? So let's look at the classic example as shown on my slides. For instance, take a case number one, a glass rod wrapped with a silk, like a cotton silk, okay? The silk has a stronger affinity for electrons than, a glass. So when wrapped together, electrons leave the glass and jump onto the silk. So the glass rod is left with a positive charge. You can see from the illustration on the slide, okay? There is a kind of transfer of those electrons when these two materials are in contact. Okay? However, take a case, for instance, about the ebonite rod wrapped with a wool. The same process took place. It has a very high electron affinity. So when wrapped with the wool, the ebonite strip electrons away from the wool, so leaving the rod with a net negative charge. So we can see that no charge were created. We simply move existing electrons from one object to the other or to another. This is the law of conservation of charge in action, as we previously explained in our recent lectures we uploaded. So very quickly, take a case number 3, charging by conduction, or number 2, sorry. So conduction means, we're talking about contacts. When there is a contact, So now let's move on to the second case. Okay, if friction is about rubbing two materials, conduction is all about touching. By definition, conduction occurs when a charged body is physically touching or touch a neutral conductor. So let's look at the three steps or diagrams in the green funnel. As you can see, we have a sphere on of an insulating or put on an insulating stand with a net positive charge. Okay, what happened? So when we bring this charged sphere into direct physical contact with a neutral conductor, you can see that it's just like we touch it, you know. So there is a separate, you know, the charges spread into the next sphere. So what happens? Because opposites attracts and like charges repel. So that is the case. So the charges want to spread out as far as possible to minimize their repulsive forces. Okay? And the second case, electrons from the neutral sphere will rush over to the positively charged sphere. Okay? So once they spread, both spheres are left with what? The same sign of charge. So in this case, both are now positively charged. So this is the case you can see in the case of conduction. All right? So the key important idea here for conduction, the neutral object always acquires the same sign of charge as inducing charge body. Take note of this at the bottom of your head, mind. Okay. So if you touch a neutral conductor with a positive rod, the conductor becomes positive. If you touch it with a negative rod, it becomes negative. So this is all about conduction, contact, in other words. Then the case number 3 is charging by induction. This is very important area of application, especially in physics. So this is what? Contact without contact. Sorry. Yeah, without contact. We are talking about charging by induction. In other words, without contact. If you remember, the previous case is about contact. So this case is without contact. Now, this third method is where physics gets really, you know, more interesting. With induction, we charge an object without any physical contact between the charged body and the conductor. So how on earth is that possible? This is the question. So let's walk through the 4 steps shown on my slides, like the purple color. That is the last method we are talking about. So imagine we have neutral metal sphere on an insulating stand. We bring a negatively charged rod close to it, but we do not let it what? To touch it. So no contact. In the case number 2, even though there is no contact, the electric field of that negative rod is highly influential to the extent it repels the free moving electrons inside the metal sphere, pushing them to the far side of the sphere. This leaves the side closest to the rod with a positive charge. I hope you are getting this point clearly. So this temporary state is called polarization or charge separation. So the sphere is still, you know, somehow neutral overall, but it is charged. Its charges are somehow polarized. Yeah. Okay. So the final step, what will happen, or the third step, what will happen? There is a case. Okay, now while the charge rod is still held in place, we connect a grounding wire to the side of the spare where it repelled electrons are what somehow gathered. So the earth is massive, practically infinite. It's just like an infinite reservoir of charge. So what will happen? Those repelled negative electrons, seen, escape to the root to the ground and rush down to the wire in the earth. It's just like we have tapped some electrons and trying to divert them through the earthing. Okay, so this is case number 3. On the final case, we disconnect the ground wire, trapping the remaining charges on the spare. Then we finally remove the charge rod. Because some electrons escape to the ground, the spare now has a permanent deficit of electrons. So that is why if you look at the final spare, it is left with a net positive charge. And you can notice that in conduction, the spare got the same amount of charge as the rod. In conduction, the spare ended up with the opposite charge of the induction rod. So this is a classic example. Maybe we normally ask the students in the exams questions. So make sure note that maybe take note of these differences. Okay. So in summary, you have to remember that charge can be transferred via friction, conduction, or induction. But throughout any of these processes, the total charge of an isolated system remains absolutely constant. We are only redistributing what it is already there. That is what I want you to recall, number 1. Number 2, remember, like charges repel and like charges attract. This is simple fundamental law which we have previously explained in the course of our lecture. So, the driving force behind all these 3 charging methods involves a force. Okay? So, maybe briefly, before we proceed on how we calculate these electrostatic forces mathematically, you can maybe ask any questions on our previous lecture so that we explain it more. In case if you have some areas of difficulty in understanding what I'm trying to explain here. Okay, so for today, this is our lecture, and we'll see the possibility of uploading the subsequent slides and explaining it briefly. In this way, we can save much of our time, and you guys can have chance to, follow it off at your comforts. Okay, conveniently. Thank you, and have a great day ahead. Thank you very much.